And the meeting will be recorded. Apparently my connection is unstable, but we have been more unstable than that. So it looks okay from here, and I'm close to the router, so it should be fine. So going to start. Take a deep breath. So welcome everyone. We're going to have our third live lecture, and I hope you'll be able, or that I hope you are following so far. And we have covered the following, and that's what we're going to discuss in this lecture. So first, we're going to go briefly and review position and momentum representation. Then we're going to talk about measurement, then density matrices, then compound systems, and entanglement. If you want to see all the asynchronous lectures that have already been uploaded, you can use the hashtag, but I'm going to release them slowly. This is still an issue. I do apologize for the situation. I've tried to hack into this from all sides. I put everything on Dropbox so that at least the intercollegiate students are not that harmed. At least you have access to the videos. So the link is in the forum and you'll be able to see. And what I managed to do is to compress the files so that hopefully LectureCast, not LectureCat, is not gonna crash. But we have to see. Fingers crossed. I'll let you know as soon as I can whether there are some new developments. So how are we going? In the asynchronous lectures, we have covered the following. We have looked at continuous variables, position, momentum. Now, okay, waiting room. So pretty much what we're going to have and what we are covering is related to compound systems, tensor product, entanglement, also how we prepare mixed states and how we use a density operator and density matrix. This is something that is going to be for next week, this last part, but we're doing well with regard to quantum mechanics from the ground up. And come on, move. I hope you have tried this at home. Remember that we had a few things that I said, do try this at home. So before we start going through all this, I'm going to go very quickly and discuss what I said. Okay, try this at home and we'll have a look. Okay, remember that we had something related to unitary transformations and operators. And I had asked you to verify that an operator U, which was given by this form, is going to give you this transformation from the basis psi I to psi I to phi I, and that this was unitary. And the main point of wanting to have a look at that was because in the asynchronous lectures, you can see that there is a really convoluted way of doing this using the matrix representations of operators. And I wanted to make the case to you that things can be much faster and actually simpler if you explore all the power of the Dirac notation. So how do we do this? Well, so let's compute psi I, beta said u psi I. So we know u, we were given this to psi I. When you do that, you have this cat here and you apply this bra psi k to psi I. This is going to lead you to Kronecker delta ki, and you end up with this expression u psi I is going to be sum over psi over phi k delta ki, and this Kronecker delta is going to kill the sum, so the only term which is going to survive is the one for which k is equal to I, and you get your reply. So you can see that you've shown that this operator satisfies unitary transformation and takes the system from psi I to phi I fairly quickly. And if you use this notation, it's something that is just like a couple of lines. I just have this line here because I was pedantic, but I could have done it in 3 lines. Also, how do you show that U is unitary? Okay, so to show that this is unitary, you have to show that U dagger U is the identity operator. So we calculate U dagger, and you just have to swap here bras and cats. So you calculate U dagger U. So you end up with psi k, phi k, phi j, psi j. You have then this inner product here. Again, we're using the fact that this base net is expected to be orthonormal. And from this condition, we get once more a Kronecker delta, and we get a closure relation in psi. Can you see? Because this is the identity operator, we know then that U dagger U is the identity operator, and that therefore U dagger is U minus 1. So this once more shows you, if you look at, compare this proof to the proof in the asynchronous lecture. And 2 things you're going to get from here. That Dirac notation, if you can use it in an abstract way, is really powerful. And that closure relations are also very useful, and they are pretty much everywhere. Another thing that we said, okay, give it a try, is we had already shown in an asynchronous lecture that for a Hermitian operator, distinct eigenvalues correspond to orthogonal eigenvectors. No, we hadn't shown. We had shown that the eigenvalues were real, that if the operator is Hermitian, the eigenvalues are real. This we shown in an asynchronous lecture. So now what we're doing is we're showing that for a Hermitian operator, distinct eigenvalues correspond to orthogonal eigenvectors. So I'm going to use the hermiticity of this operator. I'm assuming that I have this L, which is a Hermitian operator. I apply this to this A lambda M, A lambda N, which are supposed to be eigenvectors of this Hermitian operator. And I get distinct eigenvalues lambda M and lambda N. Just eigenvalue equation, okay? Now, if you take the Hermitian conjugate, you see, you apply this to the bra. Note here that L dagger is equal to L, so I'm using hermiticity already here, and that the eigenvalues are real, so I don't put lambda star or lambda M star or lambda N star. I just put this, so I'm using the fact that the eigenvalues are real and that L is equal to L dagger, right? Which are things important if you're dealing with hermiticity. Then you get this guy and you multiply by the bra A lambda M from the left. Gives you this. correct? So we have this inner product here and coming back to this. Then we have now this other expression which we derived when we took the Hermitian conjugates. We can multiply by a lambda n from the right. Note that this eigenvalue is different. We are assuming that lambda m is different from lambda n. So you get this. We're using here hermiticity because this expression here can only be written in this way because of hermiticity, because L is equal to L dagger, and lambda m complex conjugate is equal to lambda m because they're real. So you subtract both, you have 0. And on the right-hand side, you have lambda m minus lambda n, and you have this inner product, right? So if you look at this, you have two possibilities. Either this is equal so that the whole thing vanishes, or this inner product is 0 if they are different, which means if they are equal, this is not going to vanish, but if they're different, this is going to vanish. So you have orthonormal and orthogonal eigenvectors. So this was the proof that hermiticity actually guarantees orthogonal eigenvectors. Then we also said, try this third one. And this third one was related to a time-independent Hamiltonian, and you wanted to prove that this guy satisfies the time-dependent Schrödinger equation. And we said, use the series expansion, because in the asynchronous lecture, we did this, but we considered a very general case when we proved that it satisfies. It has to satisfy if the Hamiltonian is time-dependent, time-independent, or whatever it is, it has to satisfy, because that's how the system evolves, and this time evolution operator is going to take your system from a T0 to T. But we said, okay, I could see that there were some struggles and some issues with how you deal with functions of operators, so let's give it a try. And what you would have to do then is to get this x. Here I'm taking from 0 to t, okay? I just set my t0 to 0, but you could take any t0, it would be the same because you differentiate with regard to t. So you expand this in series, you take the derivative. When you take the derivative, you find then that you are going to have minus I h, and you have all these guys. So pretty much you can write this as minus I h divided by h bar, exponential of minus I h bar t over h. And see here, you're going from j minus 1. So it's okay if you have 1 here, because your series is going to go anyway from 0 to infinity. Because you set this j equal 1, but you have here j minus 1, j minus 1, j minus 1, j minus 1. Okay, so this implies directly that this should hold, because we are differentiating, and that you should get this kind of expression. Okay, so these were things that there is something going on. Hang on. I keep on saying I need a co-host. So it's essential to take, no, it's not. It's not essential. This is only if you don't believe that. You have to be careful, obviously, when you have something more crazy like commutators involved and so on. But you can treat it as a function. So actually, if you look at the derivation that it is written in the asynchronous lecture, you see that I just used u And I knew how U was varying, and I had the expression for U, remember? And I knew what it was supposed to do. And it was like a very abstract and a very general derivation. So this is a particular case, but I wanted to explain to people how you deal with functions of operators. You just have to be a bit careful on how you apply these things when you have, for instance, functions of operators that don't commute. It can be a bit tricky. But otherwise, yes, you can just treat it as a function. You have just to know what you can get away with and what you cannot.
Thanks.
You're welcome. So, but this is one way of proving it for a specific case. This, okay, yeah, because I have to close, I think. Okay. This UCL thing gets stuck when I'm using PowerPoint. I don't know why. It's very strange, the Zoom subscription. Okay, so let's go through what we have discussed. And in the part 1 of lecture 3, there was position and momentum representation. So this was an application of continuous basis, because we discussed, okay, how do you write operators and state vectors, etc., in continuous basis. And what we have seen was that where you had sums, you would have integrals, where you had Kronecker deltas, you would have Dirac deltas, etc., etc. And then I said, okay, let's get 2 examples which are very useful. And they're also instructive, because sometimes if you spend your whole life working with wave functions, it may be tough to accept or even to view that Dirac notation is something that is more general. So a very good place where we're going to find this is, for instance, it's in the notes, but you can have a look, for instance, in Koitanuji, chapter 2. And we said, okay, let's start from these 2 bases. If you consider position representation, basis R, you can see it's a continuous base, because associated with R, there are going to be some coordinates that vary continuously, right? Now, if it's a continuous base, I can say it satisfies this orthogonality relation. It satisfies, I don't know why my dyslexic friendly font does this. It is supposed to be a vector, but it makes tilde. But just that you know, okay? This is a 3D object in principle. So, and these this means that the closure relation is given in terms of integral. Now, if you talk about momentum space, again, you're going to have momenta that are going to vary continuously. It's not like spin 1/2 minus 1/2, etc. So you have a continuously varying momentum, which is associated to this basis set. And for that reason, we can also say it is a continuous basis. So you satisfy this orthogonality relation, and you satisfy this closure relation too. Now, let's consider an arbitrary ket. So using these closure relations, we can write an arbitrary ket like this. So we're writing this ket in the R representation, or we can write it in terms of the P representation. Now, this is something that I'm not going to prove here because it has been proven in the asynchronous lecture, but one thing that you can see, and I would definitely recommend that you have a look, is if you use normalization and closure relation, you can show that this is going to hold. So this means Try at home in momentum space, because I know in the asynchronous lecture I didn't do it. I just said, okay, use the same for momentum space. So give it a try. So you can see if you have this is like a vector which has some kind of coordinates. So this is pretty much this idea that wave function in position space or momentum space, it's going to be a component of your state vector psi in that basis. And this is something important because this concept of psi is much more general. It's not only a fancy way of writing these things. It's like when you have a vector and you write the vector in Cartesian or spherical coordinates or whatever coordinate, you know, you have to choose sometimes a basis to solve your problem. But the very object of your vector is something that is much more general than that. Okay? And operators is a continuous basis. Just plug one closure relation here, one closure relation there, and you get this in momentum representation and in position representation too. This is wrong with the notes. So if you want to go also to from basis changes from R to P, what you can do is if you have psi R, which is R psi, you insert here closure relation in P, you use some properties and you can change it, and you do the other way around. If you want to go from P to R, you have psi P, you know what it is, and you insert a closure relation here in R, and you can actually change that. So do try this at home. If you have the operator Px in position representation, show that you can write it in this way. This is quite useful. Okay, now does anybody have any question with regard to this? Because this is important. I'm going quickly because a lot of it is in the asynchronous lecture, but I know that many people have questions with that, and it is absolutely legitimate. Because if you work a lot with wave functions, sometimes it's something that is difficult to accept, psychologically speaking. So I'm happy to address if you have any questions with regard to that. Do let me know, either here or in the forum. So
I would have one question.
Yes.
So basically, every bracket I can write if I'm in a continuous basis as an integral over their representations, either in momentum space or in normal space.
Mm-hmm. Let's go back to that. This guy, right? Okay. Yes. So you can...
So if I
Yes.
And if I have a bracket, like an inner product, I always have this integral.
Yeah, don't forget that an inner product is a scalar, right? And actually, if you want to show that this is true, my advice is come with a psi from the other side. And then you have psi, and you show that this is, for instance, psi p psi, and you get the integral over momentum, and you can do the same here for the integral over position. So what you can really see is that these two things are equivalent. So this is like as if you have, imagine you have a vector, right? If you represent that vector in Cartesian coordinates, this would be your entry, right? And this, if you wish, would be your unitary vectors, these other guys.
Yeah.
Right? So this is, or let's say instead of having P representation, this would be polar coordinate. This would be your unit vectors, and this would be the entry that you have, correct? When you calculate the norm of the vector, you should have the same value for whatever coordinate system you choose to calculate that.
Yeah.
You agree?
Okay.
Yes.
Great. Thank you.
Okay. More. Yes, it is. He's asking if D3R is equivalent to D tilde. Yes, it is. It's because I was using a font which is apparently, I don't know, I have to hear from the other people if it's true, like more inclusive, and it destroyed my vectors. So it should be like this vector sign. I don't know why it's doing this. So it's like dr vector, which is D3R. So the font is, maybe I have to play a bit around, but the font was a bit strange, is a bit strange. So in a continuous basis, the eigenvalue is a continuous variable. Yes, it is. And this is an important point, and that's why you know that your basis is continuous. If you would, for instance, write the eigenvalue equation for P or R, you would get some P or R which you would change. So you have a continuous variable. So just make a test, get P operator, apply to the ket P, right? On the right-hand side, you're going to get P variable and the ket P. And you say that this is varying continuously. And you can do the same for R. So a big issue for continuous basis is that you don't have discrete values when you apply the operator to get the eigenvalue equation. Whereas if you have, for instance, a spin, you're going to have discrete values for that spin. Okay? How to calculate, this is in the asynchronous lecture, have a look. How to calculate PR in a general method. What you have to do is you have to use some properties of delta functions. And you using that property, you have to do some kind of orthogonality of the R and the P bases, and you're going to get that result. It's done in the asynchronous lecture, which is lecture 3 part 1, which is dealing with that. Have a look. If you still have doubts, do let me know and I can give you a hand. So we have lots of questions today, it's good. But because this is important, and it's like, I know very established and actually good people, excellent scientists who butcher the Dirac notation on a daily basis. So that's why I'm going into that much detail. Don't think in terms of matrix. If you have a continuous basis, to find the eigenvalues, what you have to satisfy is, you know, that once you have applied the operator, you should get a variable on the right-hand side. Otherwise, it's going to be messy. For instance, give it a try. If you apply P to the ket R, you're never going to have an eigenvalue equation, or R to the ket P. So in this case, it's not going to be about diagonalizing the matrix, or it may be not even be, what you see is if you have a matrix representation, what in fact you're going to have, if you want to think about it, let's go back. Why this never go back? It never goes back when I want it to go back. Let me see, let me close this. I can show you. No. Ah, went back, finally. You see, this guy, this would be the equivalent of a matrix representation of your operator A, right? Because what would happen if you had sums here and if you had discrete variables, you would get a matrix. So in this case, what you have is you have integrals, can you see? And you have to compute this guy, and you're going to have this kind of expression. So it's a bit different, but you would definitely see that it's not that easy, like you apply operator R to ket R and get the variable if you apply something that is not the eigenvector, something that is not corresponding to an eigenvalue equation. But the principle is similar if you have a look at this. Okay, another thing we have discussed more. No, it cannot. Can the eigenvalue of X have a value in Y? No, because what happens is this R space that I'm talking about is in fact a compound state space of one-dimensional continuum spaces. So what you're going to have is you have three subspaces which are going to be orthogonal, and whatever act on X, whatever operator which acts on the subspace X cannot act in the subspace Y. We're going to see this with regard to compound states. And this is also a part of the lecture, which was after measurement, or I'm not quite sure now if it's before or after density matrix, but this explains quite nicely, because this guy, where is the basis? This basis, P, or let me move this, in this case, R, this can be viewed as a compound basis of subspaces X, Y, and Z. And this operator X only acts upon the subspace X. It doesn't act on the subspace Y. So you wouldn't have anything. And they are such that they are orthogonal as well. So if you calculate inner product S, X, and Y, ket, it would be 0. Yes, yes. R is a tensor product, precisely. Have a look at the lecture on compound spaces, because it's exactly this example that I'm bringing. And this is very important, because you use this type of tensor product to put a lot of stuff together, like if you have particle 1, particle 2, X, Y, Z, all sorts of things. It's interesting, I can see that when the chat is on, my PowerPoint doesn't move. I don't understand this. Why can I not talk to people when I change my slide? Let me move this. So another point of this lecture was related to measurement. And in this form, this was really tailored to discrete systems. So we said that we have a Hermitian operator M associated with every measurable quantity. You would have the spectral decomposition, and here you would have projectors. And this would be the possible outcomes of the measurement, and the probability that the eigenvalue lambda j is returned would be this. And immediately after the measurement, you would have this change, which is a normalized projection onto the eigen subspace associated with that. And the question a lot of people had is, why do you consider this instead of just saying I collapse to the corresponding eigenvectors? Because you have to be a bit careful in the sense that you may have, for instance, degenerate measurements like what you have here. Say, if you, this is something in the asynchronous lecture as well. If you have this Hamiltonian and you have a normalized quantum state, and you say, I want to know the outcome of lambda 2, you see you have two states which are corresponding to the outcome of lambda 2. So you have a rank 2 projector. You calculate the probability, you get this. You have to take into consideration this guy. Good point. What you have to remember is that this has to be a normalized projection. So it's not an assumption as such, but it has to be consistent with what you know from measurement. That if you are going to measure, say, eigenvalue lambda j, you have to project onto this subspace associated with that eigenvalue. And if you look at the formula, what it has is normalized projection. So it's a mathematical way of saying that. And what happens is if you have non-degenerate matrices, okay, yeah, someone had a look at the non-degenerate. These, because you're going to have a rank 1 projector, is going to be just the eigenvector that's associated with that. Okay, cheers. So you can see from this expression, what you're doing is really the normalized projection. Can you see? So you had that eigen subspace associated with the eigenvector, with the eigenvalue lambda 2, and it had rank 2 because you had two possible eigenvectors that were giving you that. So when you take the measure, you're projecting onto that eigen subspace. And is a coherent superposition of two eigenvectors. Okay, now because we have been talking about continuum basis, you want to replace sums by integrals. So you have this probability of making a measurement from of the variable x, in this case, from a to b. So you have integral from a to b. And when you do that, you get, you insert the closure relation, but not really inserting the closure relation, but what you have to do is you have to consider from where to where you have your measurement. And you don't have a sum anymore, you have an integral. So we're going to calculate your probability density associated with values of x from a to b. Now, yeah, I have to close the chart again. Now we talked also about density matrices, and they are devices that allow us to account for imperfections in experimental devices or correlation, namely entanglement between systems. So they are more convenient than state vectors if you need to account for this type of thing. Because the scats that we have, they are okay if you have a system which doesn't have this kind of classical correlation. And one example that we saw was that you had an experiment, you prepared this in state psi1, probability p1, and in psi2 with probability 1 minus p1, because maybe you have some imperfect source. So when you measure the object observable, for psi1, you have this expectation value. For psi2, you have this other one, but you have to take into account these probabilities that appeared in your experiment. So in real life, you would have something like that, which is cumbersome, because what you pretty much see is that you have to use two state vectors, calculate your expectation value in terms of these two state vectors, and then put the probabilities in front. And what you would like to have is to have a single mathematical object from which you can calculate this O. And this will be a density operator, a density matrix. And one thing that we need to use for that are the traces. So for instance, if you have the trace of an operator A, this is the sum of the diagonal elements of that operator in matrix representation. You would have this orthonormal basis. You have cyclic invariance, basis independence, and linearity. Now, one thing that we use to prove or to determine properties of the matrix, density matrix, are these things. I'm not going to do the proofs here, but to have a look at the synchronous lectures. And one important point is I can see that some of you are a bit confused or also struggling a bit with regard to matrix multiplication. But do this matrix have to be square? How do they have to behave? Just think the following. A matrix multiplication, what do? You multiply the column of the first matrix that you're multiplying. No, the row of the first matrix with the column of the second matrix. So to be able to multiply two matrices, they don't need to be beautiful, symmetric, and blah, blah, but what you need to have is that the indices, the second index in the matrix, which is coming from the left, is equal to the first index, which on the matrix, which is coming from the right. So if you multiply, for instance, A and B, you have to have some kind of sum over A, I, J, B, J, K, so that the columns and the rows match. Okay, so this is what you do have to have a bit of a look, but it should be fine. I put some links in the forum for those who are still a bit struggling with that. Do have a look, because it's quite didactic. And using properties of, someone has a question, let me see. If you can use it, yeah, maybe you can plug in an identity operator there. Because what you want is you have three operators, right? And you want to show cyclic invariance over two. I think one way, I mean, I've never tried to do it, but one way I would do it is closure relation. My gut feeling is closure relation. Put a closure relation somewhere, group these operators in a way that you can apply cyclic permutation and go for it.
Thanks. Yeah.
Cheers. That's what they exist. They are there for. They're very powerful. So identity operator in the middle, boom, and then try to do the manipulation. Okay? Cheers. Cyclic invariance for 4 or more. People are getting greedy. I started with 3, then someone came with 2. Now people want with 4. Again, what I would try is try to group this. Let's say if you want to do 4, you can group 2 operators into 1 and be very careful with your matrix multiplication. Have a look. Have a look at how your indices are varying, so that you know you're not shifting things that are unshiftable. So basically, if you're multiplying things, you know in the matrix multiplication how the indices have to be, that the number of rows of the first guy have to be equal to the number of columns of the second guy. So basically, you would have, say, sum B, A, J, and then you have what I say, whatever you have. For instance, if you have, I would type, I think it's easier. If you have sum I, A, J, you would have to have then B, J, K, something like that. I'm typing because if I'm saying it is looking crazy. So if you can achieve something like this, I sent it privately to somebody. Hang on. Send to everyone. I meant this. You just have to be careful with the indices. If you note this sum that I wrote, you see you have ij, and then you have to start the other one thing that you're going to sum in a matrix multiplication with j. The indices have to match. And what you can try to do always, if you want to apply spectral these properties of traces, is try to group your matrices, see how they are. If you have too few, plug some closure relations in. If you have too many, group them and be careful with the indices. Okay? So we have shown then using these properties that the expectation value of O is trace O Ho, whereby Ho is this object, which is sum from probabilities Pj going from 1 to n psi j, where I have these projectors. And this is a bit what someone was saying, that it is like a spectral decomposition. It's a way of seeing it. Because you're going to have probabilities and you're going to have projectors, but this is more general. Because these probabilities, they can be associated with the fact that your system is, for instance, in a thermal equilibrium situation, or they can be associated with some imperfection that you have in your experiment, or with something in your apparatus. So I would say, which was, I think, the last question, that this is more general than that. But what you have is you have pretty much projectors and probabilities. And properties, do give it a try. They're so easy to prove. Hermiticity you can do in your head, because if you compute Hodega, you're going to see that you're going to swap this, which is going to be the same, and the probability is real, so the complex conjugate is going to be the probability. To have linearity is also simple. Unit traces, also you just have to sum the trace of Ho, and you see that the outcome is going to be 1 because it has to be the sum of probabilities, and is also non-negative. But do try at home to prove, but it is really something that if you look at this equation, you can really see the equation. And if you have a pure state, the density matrix of a pure state is going to consist of a single projector. Mixed states, in a mixed state, it's any state which is not in a pure state is a mixed state. So you cannot represent it as a single projector. And there is no way of representing mixed states using the state vector formalism alone. Also, this is something that I haven't discussed in a lecture, but it's an important definition, because I know a lot of you are going to quantum information and quantum optics, purity of the system. So if you have this gamma, which is trace of Ho square, this is a measure on quantum states, and is going to give you information of on how much a state is mixed. Ah, I see what you mean. If you look at this as a spectral decomposition, then the probability shouldn't be like eigenvalues. Yes, but it's more general. It would be like, because you would have like something in front and then you have these projectors. But it's more general because it's like you can put a lot of stuff in there. Just look at the examples discussed in the asynchronous lecture, like we had, I think, one which is quite interesting, related to demo equilibrium. And that is quite useful. And a pure state would require that trace of ρ is equal to trace ρ square is equal to trace of ρ is equal to 1, which you can also show if you have a single projector, that is what you're going to get. This is also, this pure mix is a good measure to see if something got entangled with something else. And it's something that it is quite useful, this definition. And do try to show that if you perform a unitary transformation in ρ, that the purity is going to be conserved. So take ρ to u dagger, transform ρ, and then see what happens to the purity. This is also should be easy to show at home. Do give it a try. Okay, now this other lecture was related to compound systems, and the key ideas were related to have systems we want to bring together. Say you have a system interacting with this environment, you have more than one particle, you have several degrees of freedom, and you want to incorporate this in a larger system. So this goes back to that question which someone asked me, but how do I do with eigenvector? Can I get y if I apply operator x on y? No, because you're not going to go to that subspace. And this is important in the sense that you can consider, for instance, two quantum systems A and B, whatever they are, and you want to combine them, and you're going to have associated state spaces. You're going to have orthonormal bases, and each of them has some kind of dimension. So when you construct a compound system, it needs to satisfy all the axioms that we have already determined and stated for vector spaces. It has to contain states as well that represent state AJ of system A and state BJ of system B, so they don't get mixed up in that way. And you also need to have a tensor product. So because you want to satisfy this, someone said when I was discussing X and Y and Z, how to do this, someone said, it's a tensor product. Exactly, it's a tensor product. So because why are you going for a tensor product? Because you don't want to make a mess in your compound Hilbert space. All those properties that you struggled to define, you still want them to be valid. So what do you do then? Then you combine them as a tensor product. And what you have is you're going to have with these base states going up to dimension dA, you have dB dimensional space with base states, bk, going up from 1, k going from 1 to dB, and you construct a state in this compound state space. So what you see is that an arbitrary state in A tensor product B would be the weighted sum of these guys, tensor products of your basis states in A and B. So it's important also that you need to use all GA times DB pairings which you can have from these two bases, because you would like them to span the whole space. Unless you have a reason not to, unless you do some projection somewhere. But if you want to construct and you want to use a basis of this, we have seen that basis is the minimal spanning set that you have for each state space. So you need to span things. So that's why you need to use all the pairings. And for instance, A1 tensor product B1 means system A in A1, system B is in B1. And you can also write this without the tensor product symbol. You can put a comma, just that you are aware that are other notations. And you can also build compound spaces with more than 2 subspaces, like A, B, C, as many as you want. Get, for instance, a big molecule. You want to include functional and electronic deal. You know, put like 3 subspaces. Or if you want to put electron 1, electron 2, electron 3, okay. So, you know, so you keep on building. I mean, if you can solve it, it's another issue, can be quite tricky, but this is powerful because you can construct larger systems from subsystems. And if you have an operator P and Q and P acts in A, Q acts in B, then you are going to have this kind of behavior. This guy is only going to act upon these cats, and this is going only to act upon these cats. So if you have an operator acting on A, it's not going to act on B suddenly, because of the way this whole thing is constructed. Imagine the mess you would have in your life if it weren't like this. So sometimes you have operators which are of this form. You have P acting in one subspace, and in all other subspaces you have the identity operator. So it's going to act as the identity in all but one subspace. And sometimes you denote them like this, and this subscript indicating the subspace in which is acting. And in the asynchronous lecture, we discussed many other items, for instance, discrete and continuous basis, eigenvalue equations, inner product, vector matrix representation of these. So do have a look, because it's in much more detail. Things are very powerful, really powerful. And one example, for instance, we did this in X space, but for instance, this was actually an exam, how you can construct the 3-dimensional state spaces spanned by the momentum coordinates, P, as a compound space of 1-dimensional state spaces spanned by Px, Py, and Pz. So this is like a situation that you have a continuous 3D state space, and you have 3 continuous basis sets, each of them being associated with the 1-dimensional P space. And it's asking you to give everything: compound eigenvectors, eigenvalue equations, and explain how the operators will act upon them. So what you have to do, you have then this compound state space EP of a 3D particle, and you can construct it by taking the tensor product of the 1D momentum spaces EPX, EPY, EPZ. So it's going to be something like this. You have a tensor product of 3 subspaces, can you see? Which is going to be then the 3D particle, or the 3D momentum space, and it's going to be the state space of a particle in this situation. Eigenvectors, same thing that you would do before. Get the basis, get the tensor product of the bases. You had bases px, py, and pz. Then you can construct your compound eigenvector p. And then if you would like to apply the operators, for instance, px, py, and pz, they act like this. So if you get px, is going to be px, so acting on the first subspace, which is subspace corresponding to this guy, and then tensor product identity, identity, and then you have here p. So you apply this on this cat, and then you get px, px. And the other ones, you just apply the identity, they remain the same. So you can show that this px is also an eigenvalue of the compound system. And this operator here satisfies the eigenvalue equation for this case. And you can do the same for the other two momentum coordinates. So this is an example of a continuous compound basis. And in this case, we took the coordinates, but for instance, you could have 2 electrons, and then you have a momentum of electron 1, momentum of electron 2. Or, you know, all these kinds of things you can construct. And finally, let's talk about entanglement. And this was the last part. Entangled states, they play a key role in quantum cryptography, quantum info, and they cannot be written as product states. This is what I mean by product states. So you have these examples here, considering compound states using 2 spin half particles. And what you can see is that these guys are factorizable, these product states. So you can actually say when, in what state a specific subsystem is. For instance, here I can say subsystem A has spin up, subsystem B has spin up. Here I can say A is down. And here, because I can factorize it, I can say that A is in this coherent spare position and B is in this coherent spare position. So this makes your life easier, because if you want to know how a system is behaving, then you can kind of factorize it. So they are not entangled. It's like one is not really talking to the other. But how about this? You cannot factorize this. So how can you say the state of particle A or B alone? Just looking from that, you cannot say. But what you can do is there are ways of extracting this information. And this was an issue, this type of system, because you can see, for instance, you have 2 spins up or 2 spins down. And there were paradoxes in which people said, okay, if you measure one spin and you know the other spin, the information has traveled faster than the speed of light. But the key is you cannot really infer this information, because you cannot really say in what state your particle is. And there are ways of dealing with this using reduced density matrices, which is something that we are going to see in this week that's starting in the next week. So thank you very much for your attention. I hope you're all fine. Stay safe. There are some questions. Hang on, I missed it. I don't know what Dropbox kept me out of the way. Ah, thank you. Yeah, thank you guys. Thank you everybody. I'll stop recording this. Stop recording and have a nice week. Stay safe. Hope you're enjoying the lecture.